Hi students, welcome to chemistry classes. So student, in the previous class, we explained about the EMF of cell, Nernst equation and cell reaction and sign convention. Okay. Today, in this class, we are going to start the next concepts. They are, first one, concentration cells. Okay. This is important concept. Concentration cells means here we have to find out the cell potential value by taking two same half cell reactions. We have to achieve cell potential value, that is E cell is equal to 0. Okay. Second one, application of EMF measurements. What are the applications of electromotive force measurements? And third one, determination of equilibrium constant from a E0 cell. This is the third concept. Determination of equilibrium constant from a E0 cell. And next one concept, that is electrochemical series and its application. Here students, electrochemical series, this is a very important concept for theory purpose as well as in a competitive exam purpose. Electrochemical series, this is a very important concept and its applications. And next one, determination of solubility product from EMF of a cell. Okay, these are the concepts today we are going to discuss. Okay student, so let us start. First one, that is concentration cells. Okay, this is very important concept. Okay, let us start with the first one, concentration cells. Here students, concentration cells. In concentration cells, we have to achieve the E cell value. Electrode potential, E cell value should be 0. Okay, E cells, electrode potential value should be 0. We have to achieve this condition, E cell value is 0, by using concentration cells. Just imagine student, there are two compartments like a galvanic cell. Okay, in the first half cell reaction, I am going to take a zinc electrode dipped in a ZnSO4 solution. That is the one half cell. Another one half cell, there also same condition apply. Okay, means there also I am going to take a zinc electrode and dipped in a ZnSO4 solution. But the concentration of these two half cells are different. By this condition, we are going to produce electricity. Okay, that is called concentration cells. The definition for concentration cells, student, the definition for concentration cells is the device. Concentration cell is the device which produce electricity. The device which produce electricity due to difference in the concentration of electrolytes, due to difference in the concentration of electrolytes from the same electrodes is known as concentration cells. Okay student, here concentration cell means the device which produce electricity. Okay, it's a device which produce electricity. How it produces electricity? Due to difference in the concentration of electrolytes. Due to difference in the concentration of electrolyte, we are going to produce electricity. And one more condition student, from the same electrode. You can imagine, this is a half cell reaction. This is a one half cell reaction. And here, the electrolytic solution we are going to take, that is ZnSO4, zinc sulfate. And in this, zinc electrode is dipped. Okay, zinc electrode is dipped in a ZnSO4 solution. And one more half cell reaction I am going to take here is, that is also in this ZnSO4 is electrolyte. Okay, here also I am going to take a electrolyte as a ZnSO4, and here also I am going to dipped same electrode, that is zinc electrode. Okay, that is zinc electrode, and I am going to apply a battery. Okay, and next one, inner circuit is completed with the help of salt bridge. With the help of salt bridge. Student, here inner circuit is completed by salt bridge and outer circuit is completed by a battery. So this is the main concept. Okay, here just imagine, student, here there are same electrode dipped in the same electrolytic solutions. Same electrode dipped in the same electrolytic solutions. The device is a device in which electricity is produced. Electricity is produced. How electricity is produced? Due to difference in the concentration of electrolyte. Then here I am going to take a ZnSO4. Here ZnSO4 concentration is, I am going to take a C1. And here concentration of this ZnSO4 solution is, I am going to take a C2. Okay, this is concentration C1 and its concentration is C2. But student, the concentration of this solution and concentration of this solution is different. Okay, that is why I am going to write a C1 is not equal to C2. C1 is not equal to C2. The concentration is different from the two different cells. So this is the concentration cells definition and the diagrammatic representation. And student, by using this we can calculate E cell value. Okay, we can calculate E cell value. Okay, I am going to write here concentration cells. These two are the concentration cells. So student, due to difference in the concentration, electricity is produced. Okay, due to difference in the concentration, due to difference in the concentration, electricity is produced. Electricity is produced. Due to difference in the concentration, electricity is produced. Now students, here there are two reactions takes place. One is anodic reaction and the other one is cathodic reaction. Here I am going to write the first one, anodic reaction, and the cathodic reaction. First one, here I am going to write the anodic reaction. Anode. In anode, which reaction takes place? In anode, oxidation reaction takes place. Anode, oxidation reaction takes place. Then student, here what is the cell reaction? What is the galvanic cell representation here? That is Zn electrode Zn2 plus, means Zn becomes Zn2 plus and salt bridge, and Zn2 plus electrode Zn. This is the galvanic cell representation of this concentration cells. This is solid, aqueous, and this one is solid. Means this is acts as an anode and this electrode acts as a cathode. One is acts as a anode and the other one is act as a cathode. Here I am going to write the anodic reaction, that is zinc becomes Zn2 plus, means in anode oxidation reaction takes place, in cathode reduction reaction takes place. Anode, first one, anode zinc, it loses 2 electron and become Zn2 plus ion by losing 2 electron. This is solid, it's become aqueous. Okay student, anode, in anode oxidation reaction takes place, zinc becomes Zn2 plus by losing 2 electron, and standard, that is E cell, standard oxidation potential value is X volt. X volts. Just imagine student, here E cell standard oxidation potential value is, imagine, X volts, and anode, second one, okay, first one anode is completed and next one is cathode. In cathode, which reaction takes place? In cathode, reduction reaction takes place. In cathode, reduction reaction takes place. Then what is the reaction in cathode itself? That is Zn2 plus, it gains 2 electron. Zn2 plus, it gains 2 electron, it becomes Zn, zinc. This is solid, this is aqueous. Zn2 plus, it gains 2 electron, it becomes Zn. This is the cathodic reaction. And here student, E cell potential value, that is standard reduction potential, is minus X volts. Minus X volt. Here I am going to take a minus X volt because there are two reactions takes place here. One is forward reaction and another one is backward reaction. If the forward reaction is positive, then the backward reaction should be negative. That is why I am going to write the standard oxidation potential is X volt, standard reduction potential is a minus X volt. So this is about the anode and cathode reactions. And student, net reaction, nothing but overall reaction. Net reaction. Net reaction. Net reaction is, just imagine, here I am going to cancel these two electron, means these two electron gets cancel each other, and Zn plus Zn2 plus, it gives rise to Zn2 plus Zn. This is solid, aqueous, this one is solid. So student, just imagine Zn2 plus and Zn2 plus and Zn. Here this Zn2 plus is from a cathode, means its concentration is C2. Okay, its concentration is C2 molar. This one is C1 molar. Okay, this is cathode, this is for a anode. Okay, cathode concentration is C2, anode concentration is C1 molar. Clear student? This is C2, it is for a cathodic concentration. This is C1, it is for a anodic concentration. This is a overall cell reaction. Okay, by using this, we can calculate the concentration cell, that is standard cell potential value. Okay, by using this reaction. Okay, take it down and let us start. Let us find out the concentration cell, that is standard potential cell. So student, here we are going to find out the standard electrode potential, that is E naught cell. Standard electrode potential, that is E naught cell. E naught cell is equal to standard oxidation potential plus standard reduction potential. Okay, standard electrode potential is equal to standard oxidation potential and standard reduction potential. Okay, then what is the standard oxidation potential, student? Here, standard oxidation potential, that is E naught cell Zn becomes Zn2 plus, means here oxidation takes place, plus standard reduction potential, that is E cell, nothing but electrode potential. Here I am going to take a standard electrode potential, means E naught cell. E naught cell is Zn2 plus becomes Zn. Okay, SRP, standard reduction potential, that is Zn2 plus becomes Zn. So student, here first one, standard oxidation potential is what? Standard oxidation potential is X volts. Standard oxidation potential is X volt. And what is mean by standard reduction potential? Here standard reduction potential is minus X volt. Then E naught cell is equal to, what is the value? We will get a 0. Standard electrode potential value should be 0 for a concentration cells. Okay, this is about a concentration cell concept. Standard oxidation potential, standard reduction potential. Here standard oxidation potential means zinc becomes Zn2 plus. Standard reduction potential means Zn2 plus becomes Zn. Standard oxidation potential value is X volt and standard reduction potential value is minus X. X minus X, nothing but 0 means standard electrode potential value is 0. This is about a concentration cells. Take this. Next concept, student, that is application of EMF measurements. Next concept, that is applications of EMF measurements. Applications of EMF, electromotive force measurements. So there are so many applications are there, in which I am going to explain some of the applications. They are, first one, EMF measurement. The first application of EMF measurement is to determination of pH of a solution. Determination of pH of a solution. Determination of pH of a solution. And second one, determination of second application of EMF of measurement, determination of valency of unknown ion. Determination of valency of unknown ion. By using EMF, we can easily determine the valency of unknown ion. And third one, student, determination of solubility of sparingly soluble salts. Sparingly soluble salts. By using EMF, we can easily determine the solubility of sparingly soluble salts. And the next one is fourth one, that is determination of potentiometric titration and determination of equilibrium constant. Okay, the fourth one, determination of, by using EMF, electromotive force, we can easily determine the determination of equilibrium constant, that is K. Equilibrium constant. And last one, by using electromotive force, EMF, we can easily find out the potentiometric titration values. Potentiometric titration values. Potentiometric titration values. So these are the applications of EMF measurements. First one is determination of pH of a solution. Second one is determination of valency of unknown ion. Third one is determination of solubility of a sparingly soluble salt. And next one, determination of equilibrium constant. And last one, potentiometric titration. So these are the applications of EMF measurements. Take it down. Next, one more concept, that is determination of equilibrium constant. Determination of equilibrium constant. Determination of equilibrium constant from E0 cell. Determination of equilibrium constant from E0 cell. So this is the simple expression, determination of equilibrium constant. So student, here equilibrium constant means K. Equilibrium constant means K. Determination of equilibrium constant from E0 cell. Simple, it is a very simple derivation. So here student, according to Nernst equation, what is the expression, student? E cell is equal to E0 cell minus 2.303 RT by NF log Q. This is the expression of a Nernst equation. Student, E cell is equal to E naught cell minus 2.303 RT by NF log Q. Here log Q means it is a reaction coefficient. At equilibrium, next one more condition, at equilibrium. Equilibrium means both forward and backward reactions are same. At equilibrium, here E cell value, at equilibrium E cell value is 0. At equilibrium E cell value is 0. And student, Q is equal to K. Q is equal to K. Here I am going to write the K instead of a Q. Right? At equilibrium, E cell is equal to 0, Q is become K. K nothing but equilibrium constant. So student, just substitute these two values in the Nernst equation, you will get a expression. Just substitute these two values in equation, that is not the Nernst equation. E cell value, what is the E cell value? 0. 0 is equal to E naught cell, right as it is, E naught cell minus 2.303 RT by NF log, instead of Q, I am going to write a K. Yes, Q nothing but K. Okay. 0 is equal to E naught cell minus 2.303 RT by NF log K. Just bring this log K this side. Log K is equal to NF E naught cell. Log K is equal to NF E naught cell divided by 2.303 RT. Divided by 2.303 RT. Student, again, you are very familiar with this equation, that is 2.303 into R into T divided by F value. F value nothing but 96,500 Coulomb. That is a Faraday's constant. Here student, 2.303 RT by F, that is the value 0.0591. Then you can write log K is equal to E naught cell or N E naught cell divided by 0.0591. Student, here log K is equal to N E naught cell divided by 0.0591. I will write here log K is equal to N E naught cell divided by 0.0591. 2.303 into R into T divided by F, its value is 0.0591. Now, you have to find out the K value, that is the equilibrium constant. K is equal to anti-log. Okay, log, if you bring the log this side, it's become anti-log. K is equal to anti-log N E naught cell divided by 0.0591. This is the mathematical expression for a equilibrium constant, determination of equilibrium constant from E naught cell. So student, here larger value of E naught cell, okay, larger value of E naught cell indicates the higher tendency of a reactant to go into product. So this is the one more concept, that is the determination of equilibrium constant from a E naught cell. Take it. And students, one more very important concept, that is electrochemical series. Electrochemical series. Electrochemical series is nothing but it is a series of elements. Here I am going to write here. Series of elements arranged in the increasing order of their standard electrode potential or standard reduction potential value. This is known as electrochemical series. By using those electrochemical series, we can easily find out which elements undergo reduction and which element undergo oxidizing easily, and which elements they act as an anode and which elements they act as a cathode easily, and which elements are most reactive and which elements are less reactive. Okay, and this is very important concept, electrochemical series. Very important concept, that is electrochemical series. Electrochemical series. Electrochemical series and applications of electrochemical series. Student, the first definition I am going to write here, electrochemical series, nothing but the arrangement of elements in the increasing order of their standard electrode potential. Standard electrode potential or reduction potential, standard reduction potential is known as electrochemical series. Electrochemical series. Student, very important question may arise from this concept, electrochemical series. Electrochemical series, these are the arrangement of elements in the increasing order of their standard electrode potential. Means here there are so many elements, they are arranged in the increasing order of their electrode potential or a standard reduction potential. Here I am going to represent some of elements like here lithium, sodium is greater than potassium. Lithium, potassium, sodium. Iron, nickel, platinum, not platinum, it's a lead, Pb, and hydrogen, copper, Ag, argentite, Au, arum, and last one is platinum. So student, this is the electrochemical series. Lithium is more reactive than the potassium, it is more reactive than the barium, it is more reactive than the strontium, and it is more reactive than the calcium, sodium, magnesium, aluminium, manganese, zinc, iron, nickel, and lead, hydrogen, and it is more reactive than the copper, silver, gold, and platinum. So this is the electrochemical series. Or simply you can remember like this: lithium and potassium, barium and strontium, calcium, sodium, magnesium and aluminium. I'm going to skip some of the elements, and zinc and hydrogen and copper and Ag, Au, and last one is platinum. Okay, so this hydrogen, it is a boundary. It's a boundary for different applications. So student, here first one: lithium, potassium, barium, strontium, calcium, sodium, magnesium, aluminium, zinc, hydrogen, copper, silver, gold, and platinum. Okay, so I will write here hydrogen. After this, copper, Ag, and next one Au, and next one platinum, means gold and platinum. So student, there are some applications are there. Applications are, first one, above the hydrogen, these all are most reactive metals. Okay, above the hydrogen, these all are most reactive metals. First one condition, these all are most reactive metals as compared to below the metals present, below the these metals of hydrogen. So here these are most reactive, these are less reactive. The elements, the metals present above the hydrogen are most reactive, the metals present below the hydrogen are less reactive. And second point, that is the elements or the metals present above the hydrogen are most powerful reducing agent. Most powerful reducing agent. Reducing agent. So here these are less, these are powerful reducing agent and these are powerful oxidizing agents. These are oxidizing agents. These are oxidizing agents. I will write here second one. I will write here first one. The elements or metals present below the hydrogen are first one, that is less reactive. That is less reactive. And next one, student, that is second one, they are oxidizing agents. They are oxidizing agents, means more powerful reducing, most powerful oxidizing agent. For example, F2, fluorine. Fluorine is the most powerful oxidizing agent. Okay, so metals or elements below the hydrogen are less reactive and most powerful oxidizing agent, and metals or elements present above the hydrogen are most reactive and most powerful reducing agent. And one more, the metals or elements present above the hydrogen, they act as a anode. It acts as a anode. Acts as anode. And here, student, the metals or the elements present below the hydrogen are acts as a cathode. Acts as a cathode. That's why in the first lecture, I already explained zinc is more reactive than copper. Zinc is more reactive than copper. Okay. So student, lithium, potassium, barium, strontium, calcium, sodium, magnesium, aluminum, zinc, and hydrogen, copper, Ag, Au, and Pt. Here above the hydrogen, these all are most reactive and most powerful reducing agent, and these all are act as a anode. And the elements or the metals present below the hydrogen are less reactive and oxidizing agents, and they act as a cathode. Okay, so these are the concept about electrochemical series and applications. I am going to write the applications here. Students, these are the applications of electrochemical series. Here, the first application, that is to compare the relative oxidizing and reducing powers. First application, to compare the relative oxidizing and reducing power, means we can easily find out which is most powerful reducing agent and which is more powerful oxidizing agents, like this. Here, first one, elements present above in electrochemical series are good reducing agents. So student, in I already wrote those electrochemical series. Elements present above in electrochemical series are good reducing agents, and reducing power decreases. Okay, when you go from the top to bottom, reducing power decreases and oxidizing power increases from top to bottom in the series. Example, fluorine is the most powerful oxidizing agent and lithium is the most powerful reducing agent. Students, again I am going to read here. Elements present above in electrochemical series are good reducing agents, and reducing power decreases and oxidizing power increases from top to bottom in the series. Example, fluorine is the most powerful oxidizing agent, lithium is the most powerful reducing agent. And second application, to compare the activities of metals, means which is more active and which is less active, like this. Okay. First one, to compare the activities of metals. As we go from top to bottom in the series, activity of metal decreases. As we go from the top to bottom in a series, activity of metal decreases. For example, zinc is more reactive than the copper. That is why zinc easily displaces copper. And last one, third application, that is to decide the nature of electrode. To decide the nature of electrode. Metals above the hydrogen in the series acts as a anode. Metals presents above the hydrogen in the series, they are acts as a anode, and that at lower acts as a cathode. Anode and lowers acts as a cathode. Zinc acts as an anode, copper acts as a cathode. Student, here I am going to write some electrochemical series. You can observe here: lithium, potassium, barium, strontium, and zinc, iron, and hydrogen. This is the bridge, okay, in between reducing agents and oxidizing agent, and most reactive, less reactive, and anodes and cathodes. This is the bridge. Hydrogen, after this copper, and Ag and Au, and last one is platinum. Yes, friends. So this is about a electrochemical series. Important concept. Take it up.